Hello, my name is Valerie Stolf, and I will be reporting my results and observations for Physics 2212 Lab 3, Magnetic Field of a Bar Magnet. The purpose of this lab was to determine the distance dependence of the magnetic field of a small bar magnet for the parallel and perpendicular axes of the magnetic field. From here, this information would be used to calculate the magnetic dipole. During this experiment, a cell phone was used to measure the magnetic field distance dependence by locating the magnometer chip in the phone to provide a visual reference for understanding how magnetic fields work. These values were compared to theoretical values modeled using VPython. To complete this experiment, principles from the Biot-Savart law, superposition, and understanding Earth's magnetic poles were used in calculations. Overall, I found that the distance dependence of the magnetic field is equal to negative 2.8079, and the magnitude of mu being 1.89 ampere meters squared. During the experiment, I observed that when the manometer was far from the magnetic field was approximately 0 in the x direction. This was due to Earth's north magnetic field. When the manometer was close to the bar magnetic field would increase in the x direction. For the off-axis measurement, or perpendicular measurement, I found that the off-axis magnetic field was the recorded measurement minus the Earth's magnetic field. To determine the exact location of the magnometer chip in the phone, both of these maxes and mins for the on and off-axis distances were needed, as shown in the schematic below. The tables on the left show my measurements for the parallel on-axis magnetic field, and the bottom tables show the off-axis perpendicular magnetic field measurements. The XY plot to the right shows the averages of the magnetic field in the x direction as a function of the distance from the magnet, r. This plot is shown as a natural log versus natural log plot to show a linear relationship. This slope equation for the natural log of magnetic field on axis was used to calculate the value of n and the value of mu. Using that slope equation, it is evident that the n value is equal to the slope of the line at a value of negative 2.8079. This makes sense because, as shown in the equation for the magnetic field of the dipole, n would be expected to be negative 3 to place the r vector in the denominator. From here, I calculated the value of k in order to set the k times r to the nth power equation to that of the dipole axis magnetic field. Rearranging the equation to solve for mu and plugging in values for the constants mu naught and pi, I found that mu was equal to 1.89 ampere meters squared. To build the computational model, lines 21 to 25 were edited to build the magnetic field as the distance vector of the bar magnet. B is defined using the equation for magnetic dipole on the parallel axis. Line 31 scales the magnetic field arrows to make each arrow visible relative to others. I found a scale of 850 worked best. Lines 37 to 42 edited the axes for the magnetic fields. 37 and 38 represent the on-axis distances. Lines 39 to 42 create the perpendicular axes based off of the off-axis measurements. Lines 46 to 76 simply define the magnetic field values at the different axis locations to visualize the difference in the magnitude and direction of the magnetic field at the different observation locations. Lines 88 to 92 built a 45-degree angle magnetic field to give the comparison magnetic field value to our experimental observations. This glow script visual is depicted here along with the distances on each axis and the magnetic field value. The orange arrows represent the on-axis measurements and the teal arrows represent the off-axis measurements. The green arrow in the top right corner of the image is the magnetic field at the 45-degree angle observation. This value equates to 6.42 times 10 to the negative 6 in the x direction, 1.93 times 10 to the negative 5th in the y direction, and 0 in the z direction. Overall, it is evident that the magnitude of the magnetic field from the bar magnet decreases when the distance from the magnet increases. When the magnetic field is computed along the 45-degree axis, the distance is 0.2621 meters from the magnet's location. From the experiment, the magnetic field of the bar magnet was found to be 1.56 times 10 to the negative 5th in the x direction, 1.36 times 10 to the negative 5th in the y direction, and 0 in the z direction, with the units measured in teslas. From the computational model, my results resembled what was found in this experiment. The magnetic field in the x direction was found to be 6.42 times 10 to the negative 6 and 1.93 times 10 to the negative 5th in the y direction, again in teslas. The direction of the experimental measurements matches that of the theoretical model in the x and y directions. The y magnitude is very similar between the experimental and theoretical values. The x value for the experimental calculation is about twice as large as expected from the computational model. This is likely due to errors in measuring the on-axis magnetic fields at the specified distances. To conclude in discussion, if the Earth's magnetic field in the north had not been accounted for, and an angle other than 45 degrees was chosen to orient in this experiment, the magnetic field would differ significantly from the experimental values that I found. This is because the computed values for n, mu, and k would be significantly different. And if, instead, two magnets had been stuck together and used instead of just the one, the magnetic field would increase, but the direction would remain the same since the magnets would be oriented the same. The magnitude of magnetic field would be expected to approximately double with the addition of the second magnet. Thank you for watching.